glad to be in this online session for presenting you my work, actually. So what I'm going to discuss now is some work that we did on opinion dynamics. So this is a joint work with Fabian Baumann from the University of, from the Humboldt University in Berlin. But the picture that you have here is from my place, actually, my small school of engineering that is somewhere there on the right of the picture in the middle of the Swiss Alps. So this work was published recently in Physica A. And maybe also let me quickly do some advertisement for our website, this etranselect.ch. So our group in Sion is mostly working on coupled oscillators and power grids, and you can find all our publications and all our presentations publicly available on this website. Okay, but now we're going to discuss about opinion dynamics. So yeah, it's almost in the end some coupled oscillators if you want. I mean, at least from a physicist point of view. So what do I mean by opinion dynamics? So in the end, or at the beginning, let's say, you have some group of people that are just discussing together by any means. I mean, it could be some social media, some friendship network, or just some colleagues or work network. So from these interactions, you can just draw some influence network. So in this investigation, we will consider only undirected networks like these ones. So what it means that whenever you listen to, whenever you discuss with somebody, you also listen to this guy, right? So one of the simplest models I can think of when you have this this opinion dynamics is the one by Taylor that dates back from 1968. So it's a quite simple model, continuous model of opinion dynamics, where people that are connecting together tend to average their opinion, right, by this first term here in the equation, which is just a Laplacian coupling. But according to this model, people can still have some bias in their opinion, which makes them converge to some specific value that is individual for each people in the group. So in this paper, we consider this model, but like a specific case of this model, where we have some people, the one that are in red here, that we'll call stop-bound agents, because they try to average their opinion according to the neighbors, but they also have a bias in their own opinion. And the blue, all the guys in blue are just people that are followers that just tend to minimize the distance between their own opinion and the one of their neighbor. So now from this model, actually, you'll have one subset of a node that will be stop-bound agents, and the other subset that will be, so the rest of the nodes that will be just followers. So there are two interesting questions now that naturally arise. If you think of the case of a single stop-bound agent in one influence network, you can ask on what node you should place this stop-bound agent such that you can shift the existing consensus to some desired value. How can you place this stop-bound agent to shift the consensus in an efficient way? And if you think of many different stop-bound agents, how does the structure of the influence network impact the distribution of final opinions? Or another question would be, if you have one stop-bound agent at one place that is trying to change the consensus, where should you place an opponent of this initial stop-bound agent so that you will keep the initial consensus safe, right? So these are just some numerical illustrations to show you what I just said. So in the case of a single stop-bound agent, you see that at some point, so the guy in orange is the stop-bound agent, the single stop-bound agent. At some point in time, it changes bias from 0 to 1. And you can see that in the dynamics, so all the xi, of course, the stop-bound agent change is a continuous variable to some value. And the followers tends to keep close to him, right? So now, depending on the placement of this stop-bound agent in a network, you will have different spread here. You could have like more variance or a bit less, right? Depending on the effort of the stop-bound agent to gather all the opinions close to him. And on the right, in the case of this pair of stop-bound agents, you have now two opponents. One, the blue one that is going to -1 at some t, at some time t, and the other stubborn agent, the orange one, that is going to +1. And you can see that in that case, you don't have like a final consensus as it was the case when we only had a single stubborn agent. We have now opinions that are distributed over some finite interval with some distribution. And now what we want to do is to relate the position of these two opposed stubborn agents to the distribution of the final opinions, right? Can we predict on which side like the majority of this opinion will be, rather positive or negative? So in the title, there is also this Laplacian approach. So let me quickly mention this. So in the end, you can rewrite this Taylor model using this matrix vector form. So here you have this matrix now that is just a Laplacian plus some diagonal matrix. So that's why we call it in the end a modified Laplacian matrix. So the Laplacian, as you know, I mean, this is like the traditional definition of Laplacian. It's just the degree matrix minus the adjacency matrix. And matrix K is also quite simple as a matrix because it's a diagonal matrix that is 0 everywhere except for matrix elements corresponding to stubborn agents where you have a kappa, right? So in the following, we will denote U alpha kappa, the eigenvectors of this modified Laplacian, and lambda alpha kappa, its eigenvalues. And we'll see now that actually all the dynamics and the distribution of the final opinions are directly related to the spectral properties of this matrix here. Okay, so let's start with the first case of a single stubborn agent. So again, what we want to do now is to relate like the spread in the opinion during a consensus shift to the placement of the single stubborn agent. So first we have to define some quantifier of this spread here. A quite natural way of doing that is just by looking at what we call the coherence. This is a quite simple metric in the end. You just take the integral over time of the difference, so, or the distance, if one, between the stubborn agent and the other trajectories that you have in the network. So between the stubborn agent and all the followers, take the sum of all the followers. So if this quantity is quite large, it means that in the end, the followers are quite far from the single stubborn agents during the whole transient. If it's quite small, it means that the stubborn agent shifted the consensus quite efficiently. And actually, so now the nice thing that we have with this Taylor model is that it's linear, so we can easily solve it analytically. That's the expression that you get for the trajectories of the opinions in a network. And so when you have, that's what you get if you have a single stubborn agent at node A. And of course, you can show that just by working on this matrix here. That is just in the end the inverse, the matrix element AI of the inverse of our modified Laplacian that is equal to 1 over kappa, which is quite interesting because it shows that if t goes to infinity, all the guys in the network will converge to the same value, which means that if you have a single stubborn agent, what we saw before in the plots, we'll have a final consensus where everybody's at the same value. Okay, so now using this analytical expression, you can calculate this coherence measure, right? And get this expression here. So I mean, this expression is nice because in the end, it's only related to the eigenvectors and eigenvalues of this modified Laplacian, which means that in the end, you just have to compute the eigenvectors and eigenvalues to get the coherence. But then it's not directly related to some complex network metric. I mean, we didn't manage to connect it to some complex network metric yet. So in the end, you have to look at it numerically to see if we can say something interesting about it. So what you have here are two different network generating models. On top, you have the famous Watt-Schrogas model, where we start from an initial cycle and just rewire some edges. And at the bottom, you have this stochastic block model with two different communities. And the P intra is a probability of having a link within each of the communities. And 1 minus P intra is probability of having inter-communities links, right? So different colors here correspond to different values of the coherence measure when you change actually the placement of the stubborn agent. So you can see that for some nodes, that seems quite in the end peripheral in sense of the degree. The coherence measure is quite high, right? especially in the maybe in the stochastic block model. So we just did this quick plot of the coherence measure versus the degree of the nodes. And you can see that there's some kind of correlation between the two. I mean, the correlation is not perfect, but because you still get different values of K for the same value of C. But still, I mean, if you want to efficiently shift the consensus, it seems that you have to choose nodes that have quite high degree, which might be quite intuitive in the end when you think about dynamic of opinions. So all these quantities are related to particular networks and particular placement of a stubborn agent. Actually, each of these colors correspond to different placements. So if you want to characterize a network as a whole, you have, for example, to average this quantity over all possible placements of the stubborn agent. And that's what we did in these plots. So actually we did two averaging. First, we average this coherence measure over all possible placements of the stubborn agent, and also over many realization of these small world networks in that case, so Watch-Strogatz network, sorry, and the stochastic block model network here. So we can see that, so when you increase the varying probability, the coherence gets smaller and smaller, right? So in the end, in the completely random network, it's quite easy to shift the consensus compared to the initial cycle that we had. And in the end, if you think about, for example, a clustering coefficient, you have a clustering coefficient is quite high when you still have the cycle here. So when you reduce in the end the clustering in the network, it seems that it's a bit easier to shift the consensus for single stubborn agents. And that's the same qualitative behavior that we have for the stochastic block model. Because when we have very low P intra in the end, it means that you have like one big network without communities in the end. So in the end, one big random network. But when you increase P intra, you will have two distinct communities. So in the end, two big clusters. And you can see that the coherence measure gets higher, which means that it's quite hard to shift the consensus in this model. Okay, so that's it for the single stubborn agent. Now we will move to the case of two stubborn agents, actually two opponents. So one guy that will go at -1 in his bias, and another one that will go at +1. And now we are interested in what I show here in red, which is the distribution of opinion that we have in the final state at t equal to infinity. And for example, we're also interested in the distance between the two leaders, the two stubborn agents, sorry. And maybe also like the mean value of all this opinion. Can we say which of the two stubborn agents is, in some sense, is the winner of the game? So again, I mean, as it's a linear system, we can solve it analytically. That's what you get here in equation 10. So you can see that now this term is slightly different from what we had before. Now we have one stubborn agent at +1 at node A, and the other stubborn agent at node B that goes to -1 with its bias, right? Okay, can simply take t to infinity to get the final opinions of all the followers and the stubborn agents. And oh, sorry, the nice thing actually is that you can rewrite this equation 11 just like this. And now this is quite interesting because this capital omega here is just a complex network distance. So in the end, this is the distance between B and G according to this new complex network distance that we have here. This is the distance between node A and I. So maybe let me quickly introduce you this complex network distance. So maybe some of you already know this resistance distance that was defined in this seminal paper by Klein and Randich in '93. That is defined out of the pseudo inverse. So these are just inverse, but actually these are pseudo inverse because the Laplacian is a singular matrix. So this is a complex network matrix. Okay, I can show it. And in our case, what we have is not exactly just a Laplacian, but the Laplacian plus a diagonal term. But you can still define such a distance. It satisfies all the criteria for distance. And now you don't even have to take the pseudo inverse of the Laplacian. You can simply take the inverse as L plus K is not singular anymore. And you can quite conveniently write it using the eigenvectors and eigenvalues of this modified Laplacian here. So now you can see that I have -p and not just -1 because you can define different order of these modified resistance distances, like different powers of the inverse of the modified Laplacian. if you're interested, you can have a look at that paper that we had in Science Advances, where in the end we generalized these resistance distances to powers of the Laplacian matrix, and related these distances, these centralities, to some vulnerability of coupled oscillators. Okay, so now actually, if we go back to our final opinions, this is like quite efficient way of viewing the opinions of the followers, right? What it means in the end, you just take the difference between the distance of the follower and the two stubborn agents to get the final opinion. And this allows us actually to solve this, what we call the opinion association problem. So imagine now that you just look at the sign of the follower. If it's greater than 0, you associate this follower with agent A. And if it's less than 0, you associated it with the agent B. Because remember, the bias for agent A went to +1 at some point in time, and the bias of agent B to -1. So these are just numerical illustration. Maybe I can go to this more detailed plots. So here, what we have is 2 times exactly the same network, but 2 different choices of stubborn agents, of opponent stubborn agents. On top, we have this diamond here and this cross here that are the 2 stubborn agents. And in that case, you have the cross here and the diamond here, right? So in the first case, you can see that the blue one gathered all the opinions towards him, and you can see it actually even in the dynamics, right? You can see that all the followers were shifted to the negative values actually, right? While in the case at the bottom, the thing is a bit more like 50-50, right? You can see that all the followers stayed rather in the middle, with almost half of them being negative and half of them being positive. Actually, this could be easily predicted just by looking at the distribution of modified resistance distances that you have between followers and stubborn agents. You can see that in that case, the blue stubborn agent like collected the most opinions towards him. And if you look at the distances between the followers and the blue stubborn agent, they are smaller, right? The distribution of resistance distances are shifted to the left compared to the orange one, right? So in the end, it means also, in the end, if you take the average of this distribution, it's simply the centrality computed with the modified resistance distance. So it means that as the blue stubborn agent is more central according to this modified resistance distance, it will collect more opinions towards him. While in the case at the bottom, you can see that both distributions were very similar actually. That's why in the end, the final result is a bit more equal for both stubborn agents. Okay, so that's it for this opinion association problem. Now we can go a bit in more details about the distribution of final opinions. So as I said previously, what we're interested in is to fully characterize this distribution here. So we'll look at the mean value of this distribution and at like the maximal distance between the maximum and the minimum opinion in the system, and also at the standard deviation, right? And the nice thing actually is that you can express all these quantities in terms of this complex network distance. So in the end, if you just want the Dmax, so the maximal distance in the opinions, is just given by the modified resistance distance between the 2 stubborn agents. If you want to look at the mean value of the opinions, it's just given by the difference of the inverse of the centralities computed with the modified resistance distance. And actually, that is also what I said previously. The stubborn agent with the highest centrality. So if you have a high centrality, it means that you have a very small inverse of C1. We'll gather the most opinions towards him, right? If you look at the sign. And yeah, also the variance, you can also express it using this like here second order modified resistance distance, and here these centralities. So I mean, you can express it using this this complex network metric, but this expression here is maybe slightly more involved and a bit more complicated to discuss. So maybe now let me quickly show you some numerical simulations that we did with these quantities. So in the end, what we try to do numerically is to compare, to look at these quantities, how they evolve when we tune some parameter. So again, we consider this Watch-Trogatz model where we can tune the rewiring probability, and this stochastic block model where we can tune the probability of having inter-communities links. So what you have here, for example, you can first have a look at the green curve here and the black curve here. You can see that both of them are going down with the rewiring probability. In the end, it makes sense according to what we had before, right? When you increase the rewiring probability, you reduce the distances between the nodes in the network. So it means that you will reduce the distance here, of course, if you reduce the distance between the nodes. And you will also reduce this second order modified distance here, right? And actually, quite interestingly, you can see that the mean of the average value of the mean value of the opinions is going up. Actually, but that can be explained just by the symmetry in the network, right? If you have a perfect cycle, in the end, you will have on average a vanishing mean, right? But when you introduce some long-range coupling, you will break some symmetries. So you won't have any symmetry in the opinions too, because of these rewirings, and the final state of the opinion will be either positive or negative rather than being zero on average. Okay, actually you can see like a similar qualitative behavior for the stochastic block model as it was the case for a single stub-bound agent. You can see that when you increase the probability of having intra-communities links, you also increase the standard deviation of the distribution, which means that in the end, when you have like quite large clusters in population, you will have opinions that are a bit more spread than just having one random network, right? And okay, so maybe let me go quickly to the conclusion now, because yeah, I can skip this real network application. Yeah, so in the end, what we did is that we used this Laplacian approach to connect like the spectral properties of the network to some opinion formation, right? We use the Laplacian approach because in the end you can compute things analytically, right? And again, so get some insights about what's happening in the dynamics and in the final state of the opinions, right? Yeah. So in the end, we are able to capture like the coherence of the system. So in the end, how easy it is or complicated to shift an existing consensus to some desired value, depending on the position of the single stub-bound agent in the network. And in the case of many different stub-bound agents, we were also able to connect actually most of the properties to some complex network metric that we defined as this modified resistance distance. And yeah, actually, this is quite interesting then, because you can now just look at the matrix. You don't have to do simulation of the whole dynamics. You just have to look at the matrix. So the coupling network and the placement of the stub-bound agents, and just compute then some complex network distance to characterize the final state of the opinion in the network. Okay, so that's it for me. Thank you.
No, thanks to you, Melvyn. Nice presentation. We have time for some questions. At some point, you mentioned that the location of the stub-bound agent can be important.
Yeah.
Can you comment on that?
Yeah. So actually, if you just think of the single stub-bound agent in the end, it is important because in the end, actually depends what you want to do, right? If you want to shift an existing consensus in the population quite smoothly without having too much riots, or in some sense, if you want, you would like to have all the followers quite close to you during the whole shift of the consensus. But I mean, you can also, it might also be possible that you just want to in some sense, to put some mass in the population and just select the node in the network, which will give you the largest spread in the opinions during the shift of the consensus. And that was like the idea that we had. Can we identify which node we should choose to reach either of these goals?
Yeah, thanks. There is a question. Can you read that?
Where is it?
Q&A.
Oh, yeah. do you think oscillatory behavior of the individual opinions is possible for some network topologies? Oscillatory behavior of the individual opinions. As I'm reading the question, I think it means that you will have like, for example, oscillating like bias in the opinions. I mean, in the end, we choose these opinions that were like in the box shape, just as some kind of toy model. But I guess you could also use some kind of noise or some oscillating functions in the end, which might be maybe a bit more realistic. In the end, that was just like a first attempt to try to model this like this first very simple this very simple how to say a phenomenon on opinion dynamics. But of course, then like periodic bias in the opinions might make sense, and yeah, actually it could be useful to answer all the questions.